Okay, we're going to continue with chapter 1. We're going to talk about data representation. As you work through this section, I want you to have paper and pen and pause video. Every time there's an example, work it out, make sure you understand what is being said, because you have to know how to do this throughout the entire course. So this is like the basics of something that we're going to use in every single chapter. So make sure you have paper, pen, and you practice and really understand what we're doing. In the wrong way. There we go. Okay, so we're going to be talking about binary numbers, how to translate between binary and decimal, binary addition. We're going to talk about integer storage sizes, hexadecimal integers, signed integers, and character storage. So let's start with binary numbers. So we said binary numbers are digits 1 and 0. Just keeps moving, sorry. 1 is true, 0 is false. So right here, you see a binary number, okay? Each one of these ones and zeros is called a bit. So this 1 is 1 bit. So here we have 16 bits. We start at 0, end at 15. What we call this very first number on the left, we call that the most significant bit. And the last one, if you want to call it the last one on the right, we call it the least significant bit. And this is how we number them. We number them from 0 to 15 from right to left. And all you have to think about is, like, you know, when you add numbers, just in our decimal system, like you add 10 plus 21, you add the least significant, the numbers, the digits on the right first. And so you're going to read from right to left. Same thing here. By the way, bi is a root word that means two, like bilateral, binomial. So binary numbers are base 2 system. So each digit is either a 1 or a 0, and each bit represents a power of 2. So this least significant bit represents 2 to the power of 0, which is 1. 2 to the power of 1 is 2 to the power of 2 is 4. 8, you're just doubling 16, 32, 64, 128. So each bit represents a power of 2. And here in this table, they just show you what I just said, 2 to the power of 0, and what it's equal in decimal value. Decimal value is, again, our system is the decimal system. DEC, D-E-C, is the root word for 10, like decanomial, decade, right? Every 10 years, decade. So our decimal system, we have a base 10. So once we get to 10, we carry. When we borrow 10. So this is base 2 bi. Translating binary to decimal. So when we look at a binary number, and we're going to do this a lot through the whole entire semester, so I'll say this many, many times until hopefully you understand it. It's all well in your head. So if we have this binary number here, 0, 0, 0, 0, 1, 0, 0, 1. This is 8 bits. 8 bits equals 1 byte. We're usually going to be talking about 1 byte. To convert this to a decimal number, to our system, what we're going to do is we're going to take, remember this position here, this is position 0, right? Least significant bit, and this is position 7. So this is 2 to the power of 0. This one is 2 to the power of 1, correct? 2 to the power of 2, 2 to the power of 3. So 2 to the power of 0 is 1. That's how much it's worth. Let me erase this here. So this is worth 1. This position is what the way that I'm going to explain it. 2 to the power of 1 is 2. This is worth 2. 2 to the power of 3 is 2 times 2 is, 2 times 2, sorry, not 2 to the power of 3, 2 to the power of 2. That's why it's confusing myself. 2 to the power of 2 is 4. So 2 times 2 is 4. 2 to the power of 3, 2 times 2 is 4 times 2 is 8. Okay. So this is 8. This is 6 worth 16, 32, 64, 128. So what you do is you take this 1 to the power of 0 and you multiply it times this 1. So 2 to the power of 0 is 1. 1 times 1 equals 1. Now this is 0 right here. So this is going to be 2 to the power of 1, which is 2. 2 times 0 is 0. So if there's a 0, you don't have to calculate it because 4 times 0 is 0. We're just going to calculate the ones that have a 1. So this one is 2 to the power of 3. So 2 to the power of 3 is 2 times 2 is 4 times 2 is 8. We said it was 8. So 8 times 1 is 8. Then you take these two numbers and you add them together. 8 plus 1 gives you 9. So this binary number is the decimal 9. That's what it's worth. Okay, you can go back and rewind the video, rewatch that. I'm going to show you another way that I do this much faster, okay? So I know that this is worth 1, this is worth 2. And I just memorize these, right? 2, 4, 8, 16, 32, 64, 128. So all I'm going to do very quickly in my head is I'm going to say, okay, this is 1. So 1 times 1 is 1. This is 8. 8 times 1 is 8. And then I'm going to add it together. So if I had 1, 1, 0, 0, I have this binary number, all these are zeros. I know this is worth 1. This is worth 2. This is worth 4. This is worth 8. So I'm just going to add 8 plus 4. 8 times 1 is 8. 4 times 1 is 4. 8 plus 4 is 12. So this is the number 12 in decimal format. And that's all you have to do every single time. You just have to remember what each position is worth, 2 to the power of whatever that position is, and then add it. Okay, next slide. So translating unsigned decimal to binary. So now we're going to take a decimal number and change it to binary. So we're going backwards. So when you do this, all you have to do is divide the decimal number by 2. So let's say we have the decimal number 37. We want to know what is 37 in binary. So you take the 37, you divide it by 2, and you get 18. 18 times 2 is 36. And you put the remainder. So the remainder is 1 because 37 minus 36 is 1. Then you keep dividing the quotient until you get to 0. So 18 divided by 2 is 9, right? 9 times 2 is 18. Remainder 0. Then divide 9 by 2. 9 divided by 2 is 4. 4 times 2 is 8. Remainder 1. 4 divided by 2 is 2, because 2 times 2 is 4. Remainder 0. 2 divided by 2 is 1. Remainder 0. Take that 1. 1 divided by 2 is 0, because 2 goes into 1 0 times with a remainder of 1. This here is your binary number, and you're going to write it. So the bottom number, notice, is the first number. So write it bottom up. So this will be your most significant digit. This will be your least significant digit. So 1, 0, 0, 1, 0, 1. This is the binary number for 37. And we can go the other way. We can convert it and check to make sure that we did it correctly. Remember, this position is worth 1. This one's worth 2. This one's worth 4, 8, 16, 32. 32. Remember, I'm just doubling the numbers. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. Okay, I'm just doubling the numbers. So 32 plus 4 is 36, plus 1 is 37, and it checks correctly. So anytime you do a conversion, go back and check it to make sure that you did it correctly, because you won't be able to use any kind of calculator or anything when you do this type of work. To go to the next slide, binary addition. Okay, how do we add binary numbers? So adding binary numbers, we're going to start with the least significant bit, which is the right-hand side. And just like when we add decimal numbers. So if I were to add the decimal 246 plus, I don't know, 30, then I would start with the least significant bit, right? I would add 0 plus 6, and then I would add 4 plus 3, and then the 2. Same thing here. I'm going to add the 0 plus the 1 first. So I'm going to start here, and I'm going to work this way. Now, in decimal system, when we carry, like let's say this was a 4 here. When we carry 10 at a time, because so 6 plus 4 is 10. So we would write a 0 here, and we carry 1. When we carry that 1 here, we're not just carrying a 1, we're carrying 10, right? Because that's the 10th position. So this is really not 4, this is 40, this is really not 3, this is 30. So 4, 5, 6, 7 plus 1 is 8, but it's really 80. Right? It's 80 because it's in this position. This is units. These are the tens position. This is the hundredths position. So here, when we carry, if it's more than 1, then we have to carry, because this is a binary system, base 2. So 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 1 is 2. So we have to carry. So we're going to carry that 2. So this will be 0, and then we put a 1 here. Remember that 1 represents like we're carrying 2, but we're just going to call it a 1. So then we do 1 plus 0 is 1. 0 plus 0 is 0. 0 plus 0 is 0, 0, 0. So here's how we added our numbers using binary. This is the sum of the numbers. So you can check to see if you did the addition correctly by converting this to decimal, convert this to decimal, convert this to decimal, and check to see that it adds correctly. So let's do that, and we get to practice converting to decimal. Okay, so remember, this is worth 1 to the power of 0 to the power of 1 is 2, 4, 8, 16, 32, 64. I'm just doubling 128. So 4 times 1 is 4. That is what that number is. This binary number in decimals of 4. This is 4 plus 2 plus 1, which is 7. This is 8 plus 2 is 10 plus 1 is 11. 7 plus 4 is 11. So it checks off. Again, I'm going fast. Pause it, go back, do this on your own. Write this number and write this number and add it. Make sure that you're able to add it. Make sure you're able to convert to decimal, okay? Because you're going to be doing this for chapter 1 assignment, for your quiz, for your test. So you need to practice. Okay, integer storage sizes. When we program in assembly, we're going to be using this terminology for the sizes of, for the storage sizes that we create. Okay, so like a variable. We're going to use the word byte, and byte is going to be 8 bits. It's going to be able to hold 8 bits. Word holds 16 bits or 2 bytes. Double word holds 32 bits or 2 word or 4 bytes, right? So double word, just write that down. So this is 8 bits. 16 would be 2 bytes. 2 bytes. I'm gonna put, well, I'll just put that. 2B, I'll write it out. It's very hard to write with a mouse. So 2 bytes is a word. Double word is double a word, exactly what it says. And then quad word is 16 4 times, because it's quad word. So 16 4 times is 64. So these are the different sizes that we're going to be using for our memory locations, our storage, or variable, like we've been using that word variable in high-level languages. Something that you're going to have to be aware of is going to be the range that these storage sizes can hold. So storage, if you think of storage, you think of a box, right? And a box can only hold so much depending on how big the box. If you have a shoe box, you can only hold, you know, it holds a lot less than if you have a, I don't know, 64 quart storage box. And so these numbers that you see here is the range of unsigned decimal numbers that a byte can hold. So a byte, if it's unsigned, meaning if it's positive, can hold the decimal number 0, the decimal number 1, 2, 3, 4, 5, all the way to 255. Once you get a 256, it cannot hold it. And it's going to overflow. So if you want a number that's bigger than 255, then you're going to have to use the storage, the unsigned word storage. And that can go all the way to 65,535. Now, I'm not going to make you know these ranges, but I'll tell you that we are going to work with this size a lot. So eventually you're going to know these numbers. You're going to know 0 to 255, just because we're going to be talking about, we're going to be using byte storage sizes a lot, and you'll see this over and over again. Okay. let me clear this drawing and go to the next slide. Here we go. So here at the bottom, it says, what is the largest unsigned integer, that may be stored in 20 bits? So we have 8, we have 16, and it's talking about 20 bits. What's the largest unsigned integer that may be stored in 20 bits? So notice here how they calculate these numbers. So to calculate an unsigned byte, what they do is they say 0 to 2 to the 8th, because that's how many bits are in a byte, 8 minus 1. To calculate the unsigned word, it's 0 to 2 to 16. Word is 16 bits, so you would put 16 there minus 1. So here, all you have to do is going to be 0 to 2 to the power of 20 minus 1. So you can get your calculator and do 2 to the power of 20, subtract 1, and that's going to be the range. Okay? That's the answer to that one. Okay, now let's talk about hexadecimal integers. Binary values are represented in hexadecimal. When we start programming, we're going to be looking at something called registers, which is a memory location on the CPU that we can store values. When we look at those registers, what we're going to see is we're going to see the hexadecimal representation of the binary value. We're not going to actually see the binary value. So we have to be able to convert from hexadecimal to binary, or from hexadecimal to decimal, so that we understand what we're seeing. Because when we look at hexadecimal, we're not used to looking at it. So it's very hard for us to comprehend what we're seeing unless it's pretty small numbers and we've been working with them a lot. So if you see the hexadecimal 0, that means the same thing as 0 in decimal. Hexadecimal 1 is the same thing as 1. It's all the same up to the number 9. After the number 9, when we get to 10, 10 in hexadecimal is the letter A, 11 is B, 12 is C, 13 is D, 14 E, 15 F. Now, hex is the root word for 6. We know that decimal is 10. That's our decimal system. So 10 plus 6 is 16. So hexadecimal is a 16 base system. 16 base. So that's why we go from the number 0 to 15. Oops, let's go back. Here in this table, it's just showing you, so what is 0 in binary? What is 1 in binary? Again, this is very simple to calculate, remember? Like if we calculate here 15, this is worth 8, 4, 2, 1. 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. From now on, just remember that 1, 1, 1, 1, 4 ones is always going to be 15, which is F. These are some, you definitely want to, remember. I know you can go A, 10, A, B, 11, but just try to remember like F is 15, A is 10, and try to remember what each one of these letters represent, just so that it goes by faster when you're calculating, okay? And then always remembering 1, 1, 1, 4 ones is F or 15. Okay, I think that's all I wanted to say for that slide. Okay, here we're translating binary to hex. So we have to change a binary number to a hexadecimal number. When we translate binary to hex and we have a very long binary number, we always break up that binary number into chunks of 4. And then we convert that chunk of 4 into its hexadecimal number. So I'm going to get my pen. We know that this position right here, again, is worth 4, right? I'm just going to keep doing this just because I know that it's just hard sometimes to comprehend. So we have 2 to the power of 0. That's just 1. 2 to the power of 1. That means that's just 2. That's just, you're multiplying 2 with nothing. But here you're multiplying 2 times itself. So you have 2 times 2, which is 4. And then 2 times, you can fast forward if you're like, I know this, 2 times 2 is 4, 4 times 2 is 8. Two times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So 2 to the 4th means 2 times 2 times 2 times 2. You're going to see 2 4 times. And then you keep doing this. So the next one would be 2 to the 5th, which is 32. You're just doubling the numbers. And 64. This is 2 to the power of 6. 2 to the power of 7 is 128. You can do it on your calculator and see that I'm correct. So position 0, 1, 2, 0, 1, 2. So it's 4. That's why that's a 4. This one is 8 plus 1, which is 9. This one is 4 plus 2 is 6 plus 1 is 7. 8 plus 2 is 10, but 10 in hex is A. Remember, after 9, 9 in hex is 9. After 9, we go to A, then B, then C, then D, then E, oops, E, and F. Okay, 11, 12, 13, 14, 15. Losing my pencil. Okay, so here we have, this is 4, this is 2, 4 plus 2 is 6, and this position is just 1, so that's 1. So this is how we convert binary to hex. Pretty simple. Now the next thing that we're going to do is leave that on the screen. We are going to convert hex to decimal. I'm going to erase a few things here. Okay, so there's a lot of stuff here. That's kind of confusing. I'm just going to leave this here on the right-hand side. A is 10, B is 11, like that, okay? Okay, so here, again, hex is is base 16. So remember how we did 2 to the power of 0 when we're converting? Like if we converted to binary to decimal, we did 2 to the power 0, 2 to the power 1. Well, here we're going to do 16 to the power 0, 16 to the power 1. So we're going to do 16 to the power of 0 and multiply it times 4. 16 to the power of 1, multiply it times 3. 16 to the power of 2 times 2, 16 to the power of 3 times 1. So this is the hex number. This is not a decimal number. This is hex. And we want to convert this hex number to a decimal number. This is what it's going to be in decimal. So hex 1, 2, 3, 4 is 4,660. And the way we do that is by saying Well, 16 to the power of 0 is 1. 1 times 1 is 4. This equals 4. 16 to the power of 1 is 16. 16 times 3, 16 plus 16 is 32, 48. So this is 48. This is going to be 16 times 16. I'm going to have to now get my calculator. And that's fine that you get your calculator too. So this is 256 times 2. That's 12 carry 1, 11 carry 1, 5. So that's 512. And 16 to the power of 6 would be 16 times 16 times 16, which is 4,096. So this is going to be 4,096 times 1. Right, times 1. So it just stays 4,096. So then I'm going to add 4,096 plus 512 plus 48 plus 4. And that will give me 4,660. If I did all my math correctly, which I did, that's what it equals to. And I'll show you how to check that, how to go from decimal to hex in the next slide, I think. So let's erase this and do the next example. So in this example, we have some of the letters. So this is just worth 10, right? And this is worth 11. So this will be 10 times 2 to the power of 1, and this would be 11 times 2 to the power 3. So here we start here. We always start with the least significant digit, 16 to the power of 0 times 4. Then we have 10, right? This one's 10 times 16 to the power of 1. Then we have B, which is 11. This is B times 16 to the power of 2. And then 3 times 16 to the power of 3. Calculate all that, add it together. It gives you this number. Stop the video. Do this math. Make sure that you get that number, that you understand how this is done, okay? Because you're going to have to do this a lot. This table here just is just telling you what 16 to the power of 0 through 7 equals. So you don't have to do it on your calculator. So this could be something that you have. If I give you a quiz or a test where I don't allow a calculator, then I will give you this table, or it's going to be simple multiplication, like maybe 16 to the power of 2. That's something that you can do on paper by hand. So now we're going to go the other way. We're going to take a decimal number and convert it to hex. So if you've converted from hex to decimal, you can check your work by going backwards, right? So we're saying if this is the decimal number, and so our number system, 422 in decimal number, base 10, you just divide it to convert to hex. Hex is base 16, so divide by 16. This is so what you do on your calculator, so right now, if you do this with me, right, and you do 422 divided by 16, I just did time, sorry, 422 divided by 16. It gives me 26.375. So what you want to do is you want to take that 26, forget about the decimal numbers, and then take the 26, that's going to be the quotient, and then multiply the 26 times the 16, which is, so 26 times 16 is 416. 422 minus 416, that's the remainder. So there's 6 remaining. That's our remainder. 6 plus 6 is 12, carry 1, 2, okay? Then we take this 26 divided by 16. That gives us 1. 16 only goes into 26 one time evenly. We're just looking to see how many times evenly does it get into. One time. What's the remainder? Well, if 1 times 16 is 16, 26 minus 16, right? It only goes into it once. 26 minus 16 is going to be 10. Now 10, you're not going to write a 10 here. You're going to write the actual letter that represents 10. Then 1, once you get to a 1, you're always going to get to a 1 in quotient. Then you're, it's how many times does 16 go into 1 evenly? With 0 times, 16 doesn't go into 1. So your remainder is 1. Once your quotient is 0, you're done. This is your hexadecimal number. Again, we'll read the number. This is least, the most significant digit, sorry, most significant digit to least significant digit. So 1A6 is your hex value for 422 decimal. Okay, let's do some hexadecimal addition. Again, with addition, we're always going to start from the right and move left. So we are adding from right to left. Get my pencil. We're adding this column first, and then we add this one. So here we're actually adding these 2 digits, and then these 2, these 2, and these 2. These are separate. So we have A plus B. A is worth 10. B is worth 11. Now this is hexadecimal. So it's base 16. Once you have a bunch, once you have a 16, you're going to carry that 16. You carry 1. So 10 plus 11 is 21. 21 minus 16 is 5. So I'm going to carry this 16 here. And the remainder is 5. So that goes here. Then I'm going to add 6 plus 1 is 7. And then 7 plus 4 is 11. I don't write 11, I write the letter B. 8 plus 8 is 16. So since it's 16, I carry 1 and my remainder is 0, right? Because 16 minus 16 is 0. 2 plus 1 is 3. 3 plus 5 is 8. 8 plus 5 is 13. Again, A is 10. So you have 10, 11, 12, 13, A, B, C, D. So 13 is represented by a D. And then 2 plus 4 is 6. 6 plus 2 is 8. 3 plus 4 is 7. So this is adding hexadecimal numbers. Again, base 16, you carry. Once you get to 16, you carry and you write the remainder. Clear all drawings. Let's go to the next slide. Okay, so I haven't really been talking about the why. Why do we need to know all this? So in programming, we represent addresses as hexadecimal numbers. If you've taken my class, I always talk about that, right? I always talk about like an address is a hexadecimal number, and I'll show you what it looks like. Well, we're actually at some point, not at the very beginning, but at some point in the class, we're going to be looking at an address and trying to figure out where the next number is going to be stored. What address will it be stored? Depending on the size. Like if it's a byte versus a word, then those are going to have different addresses because of the size. The size matters. So an important skill for a programmer is to add and subtract addresses of variables and instructions. Instructions are also stored in an address. And so that's why we also have to know how to add and subtract addresses. So here is subtraction. Subtraction, we borrow. So in the decimal system, we borrow 10. We always show it by just borrowing, by taking a 1, but really we're borrowing 10. Here's the same thing, we're borrowing 16. So first, I just want to remind you how we do this in decimal, because sometimes people do things, and they're not really aware of what's going on. So if I do 15 minus 20, that's not going to work. Wait, erase it, erase. Okay, so I want to I'll put a bigger number here. I'll put a 6 there. 15 minus 6, okay? So I'm saying take 6 away from 5, right? 5 minus 6 means take 6 away from 5. Well, you cannot take 6 away from 5. 5 is smaller. So you're going to borrow this 1 here. You're not borrowing 1, you're borrowing 10. This is in the tens place. So when you borrow this 1, this 15, this 5 becomes a 15. And what you're saying is, now take 6 away from 15. Well, 6 away from 15 is 9. Let's do 1, 1, 1, and a 3 here. Minus. So I cannot take 3 away from 1. I'm going to borrow. So this becomes a 0. This becomes an 11, right? So I borrowed 10. 10 plus 1 is 11. So this would be 8, 0, 2. All right, so same thing here. You're going to borrow 16 instead of borrowing 10. So in this case, I cannot take 7 away from 5. These are hexadecimal numbers. So I cannot take 7 away from 5. So I'm going to borrow 1 from this 7. So the 7 becomes a 6. And the 5 is 16 plus 5. So 16 plus 5 is 21. So this becomes a 21. And now I'll take 7 away from 21, which equals 14. I cannot put a 14 here. After 9, I have to put the letters. 14 is represented by the E. A, B, C, D, E, 10, 11, 12, 13, 14. And then I'll do 6 minus 4, which is 2. 6 minus 2 is 4. C is 12. 12 minus 10 is 2. This is 12, right? A, B, C, 10, 11, 12. Then A is 10. 12 minus 10 is 2. Okay. So what I want you to do is, again, make sure you understand how to do this. You want to pause the video, write the numbers down, work it out. Just watching me, it's not going to cut it. You want to make an A in this class? That's how you're going to do that. Okay. So stop the video, write these numbers, do the math, make sure you get this same answer that I just got. If you don't, go back and look at the video. All right. So here's an example of how we would use hexadecimal subtraction when we're looking at the address of 2 variables. So the question is, if the address of variable 1 is this, the address of the next variable after var1 is this, how many bytes are used by var1? So here's what they're saying. You've got this variable 1, and it takes this much space. Okay, so var1 is at this at this spot. The address of the next variable is here. If the address of the next variable is there, then the difference is going to be how much space var1 uses. So here's what we're going to do. This is the second space. This is the first one. So this is this one. So let's imagine in memory that this is how it looks. So var1 is here, and it's in this address. Here is where the next variable starts, whatever the name is. We don't know what the name is. We'll call it X, okay? So, and it goes like this. So the difference between these two is going to be how big var1 is. So we start with this number, which is the bigger number. We put it at the top. So 0, 0, 4, 0, 0. And you can do this on your own and then see if you get the answer that I get, okay? 0. Oh, not another 0. No, 6. Sorry, I'm getting tired. So this is 6a. And then we're going to subtract this number. When I get tired, I start making mistakes. So we have 1, 2, 3, 2, 0. And I'm going to subtract it. And I do 0, taken away from 4 is just 4, right? 4 minus 0 is 4. That's not a problem. So here we have 6 minus 2. Oh, that. Wait, did I miss something? Yes, I did. This is an A here. Sorry. So, easy. Okay, so this is an A. All right, so A minus 0 is A. 6 minus 2 is 4. This is going to be 0. This will be 0, 0. This will be 0, 0, 0. So I'm not going to do all the zeros. So our number that we have is 4A. So what we have to do to figure out how many bytes are between these, you're going to convert this to a decimal number. So to convert to a decimal number, you're going to say 16 0 times 10, right? This one is 16 to the power of 0 times 10, and this one is 16 to the power of 1 times 4. So this is 1, 16 to the power of 0 is 1, 1 times 10 is 10, that's easy. 16 to the power of 1 is just 16, 16 times 4, 16 plus 16 is 32, 32 plus 32 is 64, 64. So that equals to 74 bytes. That is how many bytes are between, these two variables. I'm sorry, that's how many bytes var1 takes. And the reason is, so this var1 is 74. So this address is the start, is where the actual value starts. So 004,006A is this right here. It's where this next variable begins. And then, you know, if this variable, I don't know, takes 10 bytes, then it takes 10 bytes. Whatever it takes, it will take, but that's where it begins. Okay, so this variable 1 will be 74 bytes. Okay. Signed integers. So if you're looking at a binary number and the most significant bit is a 1, then you know that it's a negative number. So this is a negative number because this bit is a 1. This is a positive number because this bit is a 0. In a hexadecimal number, if you're looking at a hexadecimal number, if the highest digit, so the highest digit would be the A, the C, the A, the 9. If it's greater than 7, 8, 9, 10, 11, 12, 13, 14, then 15, then it's a negative number. So in a hexadecimal number, if the highest digit, this digit here that it starts with, is greater than 7, it's a negative number. In a binary, if it's a 1, it tells us it's a negative number. Here, we're going to look to see how we form the 2's complement. So negative numbers are stored in a 2's complement notation. So if you have a negative number, for example, let's say that we have a number that is this number right here, 0001. And we want to find out what the 2's complement of the number is. So the 2's complement would be how we would store it to know that it's a negative number. So we know that this here is a 1. So a negative 1, right? This is binary representation of a 1. So if we have a negative 1, what's going to happen is we first take this 1 and we show it as a binary number. Then we reverse all the bits. So everything that's a 1 gets reversed to a 0. Everything that's a 0 gets reversed to a 1. After we do that, we take this number and we add 1 to it. So we say 1, 1, 1, 1, 1, 1, 0 plus 1. So then it's 0 plus 1 is 1. 1 plus 0 is 1. All these are 1s. So a positive 1, the negative of a positive 1 is all 1s. This represents a positive 1 in binary. This represents a negative 1 in binary. This is called the 2's complement. This also represents the additive inverse. So what you can do is you can take this to check that you did this correctly. You can take this number that you started with, the 0001, and you add this that you came up with, and it should give you all 0s. So anytime you do a 2's complement to a number, if you add the number you start with the 2's complement, it should always give you 0, yield to a 0. That's the additive inverse. For example, if we have, I'm going to make this shorter. I'm not going to use all the 0s, okay? So let's say we have 0, 1, 0, 1. So this is 1, 2, 4. So this is a positive 5, okay? So let's say that we wanted to know how a negative 5 is stored in binary. So a negative 5 is going to be, we're going to take this and we're going to first step reverse all the bits. 1, 0, 1, 0. This is our original number. After I reverse all the bits, I'm going to add 1 to my least significant bit. So now I have 1, 0, 1, 1. That's my 2's complement. That's it. Now to check it, what I'm going to do is I'm going to add this to this, and I should get all 0s. So I'm going to do, by the way, notice that there's a 1 here at the beginning. Okay. So Remember that negative numbers always start with a 1. So just so you know. So, okay, I'm going to add 0, 1, 0, 1. This number, the original number, to my 2's complement. 1, 0, 1, 1. And this is going to give me 0. 1 plus 1 is 0. Carry 1. 1 plus 1 is 0. Carry 1. 1 plus 1 is 1 plus 1 plus 0 is 0. Carry 1. 1 plus 1 is 0. And we carry a 1 that goes out of range, but we're always going to get 0. So you can check your work. So this is the 2's complement. This is how you would take a decimal negative number and convert it to binary. Okay, so if I have a -7, how would I convert a -7 to binary? You do these steps. First, you find 7 as a binary number. What is that? Reverse the bits, add 1. That's the 2's complement. Done. This will be the answer. Binary subtraction. Just like we've done all the other subtractions, when subtracting A minus B, you're going to convert B to its 2's complement. Oh, not like everything we've done, sorry. So here we're subtracting A minus B. So instead of doing A minus B, you're first going to take the B and do the 2's complement, and then you're going to add A plus B. So here in this example, let's see, they're adding, so they say A minus B. So this must be A, and this, I guess, must be B. No. Okay. Sorry, I'm looking to see what's going on. So we have 0, 0, 0, 1, 1, 0, 0. Okay, so first of all, let's look at the 2's complements of 1, 1, 0s. Oh, I see what they did. I got it. All right, so this is A and this is B. So they just wrote A over here again because they're going to add this and this together. And then they did the 2's complement of B. So this here is the 2's complement of B. And then they added these two together. Zero. Yep. And then this is the answer. So again, this is A. This is B. So they found the 2's complement of B. So 2 complements of B is this. And then these two were added together. So let's go ahead and subtract. Let's do this example that they have here for practice. So go ahead and do this on your own. You can do it with, and then you can see me do it, or the other way around. So we're subtracting 0, 1, 0, 0, 0, 1, 0, 1 from this number. So you have 1, 0, 0, 1 minus 0, 1, 0, 1, because you're taking this number from this number. Okay, so hopefully that makes sense. This is how it's written. So we're going to get the 2's complement of this number here and then add it to that one. So the two's complement of this one is 1. Let me move this out of the way. 0, 1, 0. We're going to add 1. That's 1, 1, 0, 1. Then we're going to add these two numbers together. So 1 plus 1 is, let me put them under it, okay? So I'm going to say 1, 0, just so you can see it better. I want to make sure you understand this really well. Add it. The 1 plus 1 is 2, so I'm going to carry that 2. 1 plus 1 is 2. I'm going to carry. 1 plus 0 is 1. 1 plus 1 is 2, so 0. And there is a 1 that got carried out, which we did not use. So if we were writing this in 8 digits, then we would add it. Then it would be 1, 0, 0, 8 bits. Okay, so always when you say A minus B, convert B to its 2's complement and then add it to A. In this chart, earlier we looked at the ranges of unsigned integers. This is the ranges of signed integers. So again, we are, you don't have to memorize these, but we are going to be using this one a lot and this one right here. And this is how they're calculated. So go through, get a calculator, and do negative, do 2 to the power 7. So negative 2 to the power 7, which is negative 2 times negative 2 times negative 2. So you got 7 negative 2's. And then do 2 to the power 7 minus 1. And this is the range that you'll get. So check those out. Those are the ranges. And again, we need to know those ranges because if you're storing a signed integer into a byte size, then you need to know that you can only store negative 128 to positive 128. So if you're trying to store somebody's age, you can use a byte. But if you're trying to store their paycheck, then you might have to use a double word, right? Unless nobody gets paid more than $32,000, which would be kind of silly, but I don't know what kind of job that, I mean, there might be a job like that, but you would use a double word. And also you want to think about your program growing. Like, for example, how long will this program be used? You know, in 10 years from now, how much are these people going to make? So you don't want to use too small of a storage size. So here you're going to practice what is the largest positive value that may be stored in 20 bits. So what you'll do is right here where it says 7 and 7, you'll put a 20 and 20. And you'll be able to calculate what is the largest positive value that can be stored. I'm sorry, it's a positive number, so you're just going to say 2 to the 20th minus 1. That's going to give you the positive number. You're not looking at the range. To the next slide. And the last thing that we're going to look at, and I know this is a lot to consume, but just so you know, like I said, and I said in my announcements, I take this into 2 different classes, okay? 2 different, 1 whole week. So, you know, you hopefully you've done that also. The last thing we're going to look at is character storage. Again, if you've taken my class before, you've looked at the ASCII table. We're going to be looking at the ASCII table. The ASCII table looks, I have it up to show it to you. It looks like this. So every character that you see on your keyboard has, it's mapped out to a decimal number, a hexadecimal number, octal, binary. I mean, you can convert this decimal number to anything, right? So when we look at characters, just a single character, when we're programming an assembly, you're actually gonna see the ASCII value of it. So if the character is, for example, the capital M right here, you're gonna see the 77 as a decimal value of it. So the character sets, we have a standard ASCII table that has 0 to 127. We have an extended ASCII table. We have ANSI table and a Unicode table. So Unicode table actually contains characters that are found in other languages. That's why it's so big. Null terminated strings, array of characters are always followed by a null byte. We've talked about that in high-level languages. So a null sometimes is just represented by the word null and ULL, or if we look at, oops. We're almost done. We just have this slide and one more. If we look at here, null is decimal 0. So that's how we represent that null character that terminates a string. And remember, string is like my last name is Serrano-Correa, so SERRANO-CORREA, null terminates my string. A string can be anything. You can have a string of letters, string of numbers, string of letters and numbers. You can have a string of any characters that you see on the keyboard. A space can be part of a string. So in the very last slide, we're just going to talk about these words. We're not going to be using this right now, but when you look at a pure binary number, that's just the actual direct binary number, 0, 1, 0, 1, 0, 1, 0. We can also take a look at that binary number as an ASCII binary number. And an ASCII binary number is a string of the zeros and ones, but it's in string format. So this is a character 0, not the actual number 0. ASCII decimal is, so you have a 65, which is a decimal number. ASCII decimal is a string of a 6 and a 5. So it's not the decimal 65. You can't add to a string. You can't subtract from a string. A string is just characters. So this is a character 6, character 5, not the decimal integer values. And then you have the ASCII hexadecimal number, which is a string of digits. This is 9C as an ASCII decimal, ASCII hexadecimal, not a hexadecimal number. So we cannot add or subtract from 9C because it's in its string format. Anything that has a double quote is always representing a string. We are going to find out that in ASCII, we can actually use double quotes or single quotes or apostrophes for a string, to show a string. We can use either one of those. Okay, we finally made it to the end of this presentation. In the next presentation, we'll be looking at Boolean operations. It's going to be much, much shorter presentation. Please take a look in your book. There's examples that you can work out these examples, go online, find some examples, make up your own problems. Then you can go online. There's converters online that convert from decimal to hex to binary and backwards, and check your problems. Your assignment You can already start your lab 1 because your assignment actually has you doing some of this stuff. Again, when you do your assignment, you have to show me your work. You have to show me how you converted it. I don't want just the answer, but you can check your answer by going to those converters and seeing if you did it right. If you didn't, then you can just start it all over again. But I've got to see the steps. I've got to see how you got to the value that you got. All right, I'll see you in the next presentation. Thank you.